All right, the last part of chapter 14, when we're talking about gas laws, right? One thing that we haven't done yet is talk about mixtures of gases. I mean, up to this point, we've only been talking about one gas at a time, right? We've covered a gas and its pressure, its volume, its temperature, its number of moles, but we haven't talked about mixtures of gases. And that's what Dalton's law helps us do. Okay? Dalton's law says that in a mixture of gases, if we have different gases mixed together, the total pressure is the sum of all the partial pressures of the gases. Seems like a really simple concept, right? So the total pressure of all of the gases is the individual pressures of each individual gas just added together. Pretty simple. So if you took, let's say we had a tank of helium here at 400 kilopascals, and we had a tank of oxygen at 100 kilopascals, and we put them together, what are we going to have? We're going to have 500 kilopascals. And there are some scuba tanks. This is what the scuba tank would be filled with, right? So if somebody wants to go scuba diving and they need to breathe, they would fill it with some helium and some oxygen. Now, you're not used to having 100% oxygen. That would be bad. You wouldn't want a tank just having oxygen in it because your body's not used to that. You need to breathe in and have only part of that gas be oxygen, which is what regular air is. Regular air is mostly nitrogen, actually, with some oxygen in it. So let's say that we had a gas mixture that contained oxygen, nitrogen, and carbon dioxide. Well, that sounds familiar. That sounds a lot like regular air. And let's say that it has a total pressure of 32.9 kilopascals. If the pressure of the oxygen was 6.6 kilopascals and the pressure of the nitrogen was 23.0 kilopascals, what's the pressure of the carbon dioxide? Okay, so let's list what we know. We know the total pressure, right? We also know the pressure of just the oxygen, and we know the pressure of just the nitrogen. And we're looking for the pressure of just the carbon dioxide. So Dalton's law says the total pressure is equal to each individual gas's pressure added up. So the total pressure should be equal to the pressure of oxygen plus the pressure of nitrogen plus the pressure of carbon dioxide. So let's fill that in. The total pressure, which is 32.9, is equal to the pressure of the oxygen, 6.6, plus the pressure of nitrogen, which is 23.0, plus the pressure of CO2, which we don't know. This is our unknown. So we have to go through and simplify. We would have to add these two together. And then if we want to move it to the other side so that we get pressure of CO2 by itself, if we move this to the other side, since it's being added on this side, we'd have to subtract that answer from the other side. And when we do that, we get 3.3 kilopascals as our pressure at the end, okay? So again, Dalton's law, pretty simple. The total pressure is just equal to the individual pressures all added together. All right, and then we have one more law, one more. The last gas law that we need to talk about is something called Graham's law. And it doesn't deal with pressures and volumes and all those kinds of things. It deals with how fast the particles are moving. Okay? Graham's law deals with something called diffusion, which is the tendency of gases to move toward areas of lower concentration across a membrane until equilibrium is established. Or, in other words, it says that gases like to spread out into their areas. That's probably the best way to think of diffusion, right? Gases want to spread out and diffuse in the area. If you remember, we did this activity in class the other week where I had some smelly stuff and I let it go into a container of hot water, boiling water. And the smelly stuff, the idea was it would start to rise up and only fill the area in the corner of the room, but then it would spread out and it would move. You've probably noticed this with like cologne or perfume, right? Or Axe body spray or something like that, right? Where if you spray it in one area, then suddenly it sort of moves out, and then people far away from you can start to smell it because it's starting to fill the area where there wasn't any of that stuff before. That's called diffusion. So if I have a gas on one side of this container and then I have something that is stopping it, closed off, and then I were to open this up, this is going to fill the area on the other side so that we have equal amounts. So that's why we call it an equilibrium is established. Now there's something called effusion, which is really similar to diffusion. The only difference is the gases are moving through a small hole, right? So for instance, let's say that you had a tire and the tire had a small hole. You ran over a nail with your tire on your bike or on your car, and there was a small hole. Well, the gas is going to start pouring out of that hole, right? Until it sort of equalizes with the gas on the other side. So if we have gas and then a little hole, some of that gas is going to start moving through that hole until it starts filling the other area until these are equal. So it's the same idea. Diffusion, effusion really are the same idea. All right, gases want to move from one place to another until they're equally covering both places. So Graham's law then says lighter gases move faster than heavier gases. Again, not a big revelation. You're like, well, that seems like it makes sense, right? If you have a person that is really light, right, and they're running against a person that's really heavy, more than likely the light person is going to win that race just about every time. Why? Because they're lighter. They can move faster. They don't have as much to carry. So lighter gases move faster than heavier gases, which means, mathematically, the rate of one gas, we'll call it gas A, compared to or divided by the rate of gas B equals the square root of the molar mass. Now, we're going to think of molar mass as sort of like how heavy these things are. So molar mass is how heavy the gas is of gas B divided by how heavy gas A is. Okay? So that is Graham's law. And then we're going to do one sample problem to kind of understand how to fill this in, what it's going to look like. Calculate the ratio of the velocity of hydrogen molecules to the velocity of carbon dioxide molecules at the same temperature. So what we want to do is we want to figure out which one's going to move faster. Is hydrogen going to move faster, or is carbon dioxide going to move faster? And the one thing that we would need to know is which one is heavier, right? And it would be really easy to do, and I know that we haven't really talked about, how to figure out moles and mass and all that kind of stuff. We haven't figured all that out yet. But there's a really simple way to actually look at what's lighter and what's heavier, and that is look up the elements on your periodic table. If you look at your periodic table, and you might want to pause right now and get out your periodic table of elements so that you can look at it while we're talking about it. Go ahead and pause. All right, you have your periodic table sitting in front of you right now. If you look at your periodic table, I want you to look up hydrogen on your periodic table. Notice it's way in the upper left-hand corner, and it's the first element listed, which also means it's the lightest element on there. Okay? So hydrogen is a very light element. Carbon dioxide, as you can tell by the name, has a couple of different elements in it. It has carbon. You can probably find carbon if you move over to the right side on the periodic table, you'll see C for carbon. Carbon's a little heavier than hydrogen is. And dioxide means it has 2 oxygens in it also. And you can see oxygen's pretty close to carbon on the periodic table there. So that means that hydrogen's really light. Carbon dioxide is going to be much heavier. Which one's going to move faster? Of course, the hydrogen is, because he's lighter. But how much faster will he move? Well, now we're going to have to put some numbers in. Okay? So what we're going to do is we're going to use that periodic table, and we're going to use the numbers that are at the bottom of each element. You notice at the bottom of hydrogen, okay, if you look in the little box where the H is for hydrogen on your periodic table, the number 1.01 is below it. That's about how heavy the hydrogen is. Okay. Now, hydrogen molecules are actually made up of 2 hydrogens. I wouldn't expect you to know this yet. That's all right. That's why we're learning how to do this. So 2 hydrogen weighs about 2 grams per mole. For carbon dioxide, we have to take the number underneath carbon, so underneath C, which is what, 12, right? And then we have to take the number under oxygen, which is, right, 16, I think. But we have 2 oxygens. 2 times 16 is 32. 32 plus 12 is 44. So CO2, carbon dioxide, weighs about 44. Look how much difference there is. Hydrogen weighs about 2. Carbon dioxide weighs about 44. Now, we want to know what are the rates of those. How fast are they going to move compared to each other? So we're going to take Graham's law, and we're going to fill in the 2 numbers that we know. We know the molar mass of H2. We know the molar mass of CO2, so we can fill those numbers in. It's 44 divided by 2 square root. So 44 divided by 2, and then take the square root of that number, gives us 4.7. So what does this 4.7 mean? That means that hydrogen is going to move 4.7 times faster than CO2. So if I turned on, so let's say a hydrogen tank of gas and a carbon dioxide tank of gas in a room, and I wanted to know which one was going to fill the room first, the hydrogen would do so 4.7 times faster than the CO2 would, because it's that much lighter. Okay? That's how we use Graham's law. Again, you're not going to have to do a lot of figuring out of masses that would be given to you right now. We'll learn how to do that later. But I do want you to be able to plug the numbers in to Graham's law and figure out what this number really is. Okay? All right. That's it for chapter 14.